So I try to be brief, which is not always easy for me. So there is a very short outline here. I want to talk about, what the cyber-physical human worlds brings new. Second one, a little bit few words about situations. Then talk about our real world, the world where we live, when we see the things, we see how they're related. And this is our objective world of reality. But other part of that is how we humans or any other intelligent agents are actually reflecting it. And the reflection, what they do, the mirror image that they do from the real world is not exactly the same for different agents. Then talk about situation control and how it's applied to cyber-physical human systems. Then about a quite interesting technology, which was several times mentioned today morning, is a system resiliency. So it's a kind of one policy matters, how you build cyber conflict systems or cyber defense systems, and the system resiliency is one of the methods, and adaptation is kind of supporting methods. Then I already mentioned about the importance of situations, so how we people understand situation semantics. And in order to back up some theoretical issues, I would like to give an example of situation control in resilient missions. And then a few words about adaptive situation control, what are the policies, how to system could adapt. One issue that I didn't include into my presentation, but like just to mention right now here, is so-called self-X systems. So systems which are self-organizing, self-adapting, so which is part of actually, not part of, but one of the parallel technologies of adaptive situation control. And then give some conclusions, and not only conclusions, but maybe in few words repeat the challenges that you asked me to do. So, example. It's a very popular example in the cyber-physical human systems nowadays is medical applications. So we see here, let's say, people who are mentally or physically disadvantaged, and how to magnify their cognitive and physical mechanical capabilities in order to give them quality life. So we see very clearly here the physical components, the human components, and the cyber components. And how these three components are interplayed to each other. In the last 5-10 years, we have seen significant advancements in sensor systems in terms of implanted and attached human sensors. So we can build some kind of physical model of human, and this is important, but even more, there are kind of cognitive models of human behavior, and we are actually, not we, but people are doing, research in kind of, measuring the potentials of the human brain, and kind of on the way of to understand not only some mechanical activities of the people, but even conceptual level. So this brings one important issue in situation control. So far, we have looked humans as agents in the control. How to control cyber-physical systems. Now, it is important that the human or humans are becoming the objects of control. One example here is a little bit from a different domain is the disaster situation control. Where we are talking, not individual people only, but we're talking about maybe thousands, maybe 10,000s, even 100,000s of people, and they are becoming objects of, subjects of control. So we are talking totally different paradigms, and we need to understand how to represent situations. I mean, the paradigms of panic or mass movement and so on. So how to model situations in the disaster management is important. But basically, you can see that the traditional loop to understand, sense, fuse information and build situational picture, do decisions, and then apply decision support and actuators in order to change the situation. And of course, you can, as I mentioned probably already, that we can go even more and talk about social worlds, so how these three, physical, social, and physical worlds should, cyber and physical worlds should work together. Few words about situations. I would like just very quietly to you to read the saying for a quite famous, what American sociologist is Thomas, what was his name? William Thomas and his wife. And actually, but the point that he makes, and he wrote the book in 1923. One of the major points of human evolution, or evolution of biological life, is that in the humans, that we people do make decisions not as a simple action and reaction to the environment, but we internalize. And he assigns or associates this internalization and making decisions, something that he called situation. I found this is one of the first scientific definition of situations. But more important is so-called Thomas theorem, which he says that if man defines situations as real, they are real. The meaning of that really means that there are different theories of situation management, and one of the first one is by John McCarthy, which he says that the goal of situation calculus is finding are logical expressions true or not, and describes the whole world. What Thomas says is totally contrary to that. And some other scientists later on in the 1980s, John Barwas, and I am using his theory of situation semantics, but John Barwas says our interest is problem solving and not necessarily describing the full universe of that. So what we do, some few examples. I mentioned about that there is a real world and there is an agent who reflects and builds his or her or its perception of the real world. This is a very important point. So we are dealing with situation awareness, and we're dealing with decision support based on so-called abstract situations. So there is a real situations and there is abstract situation. And if there is a 10 agents, they have 10 different interpretations what is the real world. So situations, more scientifically, are states of the world mapped to a time and space and how they are interpreted by agent. So if we have a real world, we notice entities and relations and the behavior of these entities in the real world. So there are different actions which affect the real world. There is natural forces, there are agents, there are adversaries, and so on. There are other systems. So the first task, what we see here, and we model these complex systems almost like as a state machines, so moving from state to state under some actions. And then the movement from one situation to another situation is event. So the upper part of this diagram exactly says that if you have a different perceiving agents, they can build different models. So the complexity actually is represented here quite nicely. But I can say very briefly here, not always the difference between the actions and events are obvious. Some people actually treat actions and events as almost similar categories. The second important thing is, which makes situation theory quite powerful, is that the actions, situations, and events are considered as first-class objects. So objects which can be separated, cognitively, which can be stored, which can be reasoned about, which can be retrieved, and actually, if you want, can be killed, deleted from the memory. So this, I'm not too much spending on time, but this is a favorite example that I got from my friend, which really means that if you have a different agents or actors playing like a cat and dog and a mouse, and there is owner of the dog, so the different agents have a different perception of the world. For example, the perception of the mouse is, as soon as a dog is playing with a cat, I am safe. While the owner of the dog looks that the cat is not coming, or the dog is not coming very active, and they can play nicely, but I have to make sure that the flower plot is safe. So there is a larger universe, which is a situation management, but I'm looking here just the situation control. So situation control is actually sensing, perceiving, and comprehending the world, and taking action so that the world moves into some certain desired situation. It could be a goal situation. So you can find here classical automatic control group, or people who are from DoD can define or see this as our OODA loop, so control loop. So there is a very specific task of the sensing, and the sensing is not only just, probably you agree with me, it's not only just signal sensing, but they are coming information from site observers. That could be natural language, the pictorial information. So you can imagine here that the task of information fusion here is quite complicated. And also, this is a living environment because it's complex systems which are acting in time. So each element, each relation in the world should be time-stamped, and we have to manage the time. We have to see when the new element became to the stage, and how the relations between the entities and the entities themselves are time-dependent. So the time management is quite important. One interesting task here is, since we are talking about symbolic information, not analytical information, we have to understand what is this goal situation. So if we have the state of the world and we have a goal situation, what does it mean to keep stability of that world, or how to move the world into desired situation? So basically, it boils down to that. If we have semantic representation of situations, and we have some specific semantic language, for example, RDF or any other, I will talk about so-called infant language, how to compare them, how to find the difference, the delta, and how to apply rules in order to either to recognize similar situations or recognize the difference between the situations, or how to move the world into desired situation. This is one of the fundamental new challenging research issues. And you can see, tasks which are past situation interpretation and prediction of the future situation, and of course, situation learning and situation adaptation, and so on, which is currently I'm just skipping from this presentation. So basically, we are dealing with the dynamic systems, both in the real world and in the cyber world. There are many interesting thoughts about how these two worlds, the dynamic, the abstract or perceived world. Perceived world exists only in cyberspace. It's an artifact. This is something which is in the brain of us humans. The cyberspace doesn't exist, physically. I mean, it has a physical embodiment, but it's artifact. So such kind of causal relationship that you can see here, moving from one state to another due to actions applied to the systems and creating events and affecting now affecting the world. This continuous loop it takes place until somebody abandons the loop, or somebody or the system feels that it is satisfied. And all the issues of resiliency and adaptation are actually taking place between these two worlds. So our physical world should be resilient. For example, in the physical world, we can talk about missions, for example, or business processes. And I will later on talk about a few words about these missions and business process. As well, our cyber world should be adaptive and self-organizing. For example, do we create one mirror image of a data or not? Do we pull data from this database, or we pull data from other database? If one data file got compromised because of the vulnerability, can we get the same data from other databases? So we establish these links between different data resources where our important information is stored dynamically. And one of the technologies which allows to build such kind of future integrated cyber physical human systems is a technology of resilient systems, which the resiliency is well-known phenomena in the natural world. It's well-known, for example, in the mechanical world. It's becoming quite well-known out in the cyber world and in the integration of cyber and physical worlds. So if we have some adverse event, we can talk about what we need to do before the event happened, during the event, and what we need to do after the event. So before the event, really we rely on predict plausible impact, what could happen. During the adverse event, we try to survive through adaptation and graceful degradation. So we heard today on the presentation morning about risk tolerance. So, adaptation and estimating risk tolerance is something that we can apply during the events. And of course, recovering. So the resiliency is kind of one of the central pieces, how to, to assure the survivability of the systems. Now, I talked a couple times that we are dealing here about meaning. And we can borrow several theories that from natural language processing, from AI, and there are different ways how to do that, how represent the meaning. One is a traditional way which has had roots in the natural language processing and goes back even to 1960s to somebody called Ross Quillian, who created these semantic graphs, basically applied to data retrieval. Later on in the 1980s, John Sawa reapplied it to, under the name of conceptual graphs, and applied to also natural language processing and some business processing. So the idea is that we represent here the entities as nodes and relations which have a semantic load. But of course, this is nice picture, doing reasoning on the graphs is very difficult. So it could be done, but it's quite difficult when the scalability becomes an issue. So there are some other ways how to do that, and I will show one way is actually to, this is a multiple relations. It's possible to complex system to decompose this collection of simple relations. And one way I will show you, it was proposed by John Barwas to represent complex relations into the set of n-ary relations, kind of specific modules, not binary, but n-ary. I will show you later on. So what's going on here? So we have a real situation on the left side. We have a perceived, also on the left side. But the original work by situation semantics by John Barwas was by natural language processing. So I took his work and try to reapply it for the situation control. The difficulty here is that the people in natural language processing say, oh, we have already natural language description. But how you get the natural language description for the real world situation, they don't care. So we, in the situation control, where we have a physical systems which act at the time, we have to sense and we have to make, we have to, to actually make sense of the data. And so we apply here situation agents. So the situation agent is a computer program which actually sends and works with comprehension and perception. But comprehension is something that you can recognize specific object. And in the perception that you can build like a mosaic from different objects and build the full picture. And the result of that is so-called collection of infons. The infon is a smallest piece of information quantity. It has a relation, like in a traditional relation, object-oriented approach, and it has objects. And there is a, if you see on the end, the parameter is I, which means is the relation true or not, does it hold or not? So that's a basic idea. The question certainly in here is now the complexity of situation agents, which, for example, is able from these raw data, which is coming from different sensors, to come up with these infon type relations. And of course, you can imagine if it's a signal processing and site per observer, or this is structured information or non-structured, and a different complexity, a different context, you can, from satellites, you can get very broad picture, but from the side observer, you get very small fragment, maybe in pidgin English or or structured or unstructured text. Put them together, the one is a quite of challenge. I have done it, but I confess you, it's not easy. So this slide simply tells that infon is a piece of information. It's important to have it, and collection of infons is called situation. And actually, if people can go into, for example, relational algebra by code, it's very similar to that. The only one thing that code didn't have a relational algebra is he didn't include time, but time is a very important part. So if we are lucky, we have a kind of situation. We collect the information, we use it, we interpret, and get this so-called abstract situation in the interpreted world. Now, I promised to talk about how the situation control could be applied to cyber physical systems, and here is one example. Example is mission control. So mission is a kind of sequence of actions undertaken to reach some goal. In the enterprise business management, the missions are called business processes. If you look at carefully, you see here two worlds. One is a real world, for example, missions carried out in some area by different agents in the battlefield, in the urban area, and there should be constant mission situation awareness and, of course, mission decision support. And this, all the mission situation awareness feeds the model of mission, in what stage the mission is. And certainly on the left side of the picture is the human control. The top part is so-called, so-called perceived world, or if we are talking about IT systems, is a so-called cyber terrain. And cyber terrain is actually, multi-level collection of information about, the network connectivity, about the data depositories to the services, and the relations between them. If one server gets knocked down by by cyber attack or crippled somewhere, we can see that how this impact propagates to a different nodes and actually goes to the support services which support, for example, database service or file service or any other service which supports the mission. So these two systems work together, and you see these two OODA loops, and they are connected. They are now independent. The top level is a situation control in the cyber world, and the low part is a situation control on the real world. So I'm not talking about the missions, you probably understand. So like as a final state machines, but multi-branching, but you can be very flexible. My time is over as usually. But did I start it later? No? Yeah. So
there is space for a resume.
So let me, I can pay you for 1 minute, for 2 minutes. So how you can use adaptation? The adaptation is, first of all, the missions have a different time order. In what order do you do that? Also, you can do sometimes one task before another task. Or sometimes you can skip the missions, some task of the missions. So the mission itself could be looked as a kind of adaptable. You can choose multiple choices how to proceed with the missions. The same thing is cyber terrain. You can actually change the links. For example, you can change the version of the database management system that you use. So you can change the nodes and you can change the links of the nodes. And the adaptability of these two processes so that the mission gets executed under the conditions of risk tolerance and resilience are these two tasks of control. They could be done by the agents because in the situation here, they're both the cyber terrain and the real-time missions are modeled like intelligent agents, which can actually talk to each other and guarantee, or at least to support the completion of the overall mission. So in the mission adaptation, we can talk of the mission adaptation, of the task adaptation, of the agent adaptation. For example, agent adaptation, there may be many different ways how to do that. For example, in the mission that we modeled in Afghanistan, either we send our team to do something, or we ask the village elders to do that. So there's two different choices, and you can choose one agent to another agent to do that. So let me now go to the conclusion, and in the conclusion, I will just quickly to repeat the things or challenges that Marcus asked. Modeling humans in situation control loop is challenge. Scalability, situation control in Internet of Things is challenge. Semantic integration of diverse domains, automatic translation among different ontologies. We still have to spend time on logic of space and time, actions, and on non-monitoring reasoning. We need to understand space, time, actions, and situations in the cyberspace, because time and space is different in the cyberspace as in the physical space. We need to look on multidisciplinary approaches across technical, strategic, legal, social, and cognitive models. And again, there are tasks of advancement of fundamental concepts, models, architectures, and theory of situation awareness and control. Thank you.
Yeah, thank you, Gabriel. And don't say like as always. I mean, we are getting better each year. So last year, I think it was 8 minutes. Now we are at 5. So maybe next year we can make it a time. Anyway, I think we will have a chance to discuss. Is there any quick question for Dr. Gabriel Jacobsen? Anyway, we will have the chance to continue this discussion because we will discuss this when we talk about the future, and this really much relates to the talk we will hear from Professor Mythos. That's why my suggestion is we will step now forward to Dr. Teller, and we all know that Fraunhofer is very close to the military domain, and that's why I actually want to ask you, now seeing situational awareness from a more military perspective in a cyber conflict, what will be the focus of future research? So we discussed active cyber defense last year at the CyCon, and I think as a follow-on, this has been discussed quite much. So do you see a trend here? Will this be a way ahead?
So the challenge for the future I see is that we don't have yet situational awareness in the cyber domain. And we have a lot of experience in physical world situational awareness, and that's really fine. We can learn a lot from this, but whenever I talk to people working in computer emergency response teams, for example, do you have situational awareness? I say, no, not really. And that's one of the future challenges to really optimize this or to give them at least a basic situational awareness. And what we learned from physical world situational awareness is that everything is geographical oriented. We heard it this morning on a ship. I have got a map, I have got symbols, I've got different colors, and I have a good imagination what's going on around my ship. And in situational awareness, sometimes it is important where the location of a system is. If you want to interact with the system, you have to know about the country it is located, who's operating it, and the laws around the system and so on. That's all really important, but in fact, quite often it's not that important how many kilometers are between system A and system B if those systems are interacting. So we definitely need another way of representing the systems and another way of making it easier to access, easier to understand how these systems are interacting.
Okay, many of you might remember we had this session on responsive cyber defense in our last CyCon, at least for the CyCon family. And we already discussed that the passive means will most probably not be enough in the future in terms of thinking cyber defense. So now really seeing this in the context of situational awareness. So what additional effort does that mean if we want to follow this approach, and how will current situation awareness system need to be adapted to go in line with this new approach?
Okay, if we have the first step of situational awareness in a static scenario, we know how our systems are, if they are healthy, if the communication is working and so on. But if we add responsive or even active measures, we need additional information about what responses we already started. Operators need to know if these, perhaps they need to know the time when they were started, they need to know the situation which occurred back in those time when we started the response, and we need to have information about if this response was successful or if we have to try another response and so on. And all this is information we have to add to the situational awareness as a whole.
Gabriel, you wanted to comment?
I wanted to know that last December the Springer issued a book called Situation Awareness and Cybersecurity. It's a book about 15 chapters by different people, and the editor is Alexander Kott from Army Research Lab. So it's a quite good first reading to grasp, what situation awareness means in cybersecurity, but I agree with what you said. It's
okay.